Can you see the screen?
Yes, sir.
So okay, first of all, in the previous class, um, I had introduced you to the chemical potential, which is basically the driving mechanism behind a reaction. So even if pressure is same, temperature is same, such that mechanical and thermal equilibrium are maintained. Still, a difference in the chemical potential can lead to a chemical reaction. We had seen this for a single component system for a phase change process. Okay, so now we will consider a multi-component system. Okay, so we will consider the case of mixture of ideal gases. So we will assume that we have a mixture of gases and the gases are ideal. They behave ideally. So what is the intention here? We want to basically predict what would be the composition of uh, the gas mixture. Okay, so for example, let's say you take in a container carbon monoxide and oxygen. Okay, this is at room temperature. Now you heat it up. So at room temperature, you know that they won't react. Okay, so nothing will happen. But as the temperature increases, the pressure in this particular case, the pressure also changes. So finally, let's say we took it to 3000 Kelvin. Okay, you can calculate the corresponding pressure. Now, what would be the composition at 3000 Kelvin? So, what will be the constituents first of all at 3000 Kelvin? What do you think? Should you be having only CO and O2 or something else you expect?
CO2 will
Any
also
answer?
be found. CO2 will also be
CO2 will
found.
be okay. CO2 will be there. It is also possible that you may have oxygen atoms. So as I had mentioned earlier, if the temperature is high, CO2 would dissociate to CO and O2, and there will be an equilibrium between the reactants and the product. So CO and O2 would combine to give CO2. On the other hand, CO2 would dissociate to CO and O2. Okay, so now the composition there, okay, is not defined by the stoichiometry. So in general, we write, right? So in this reaction, we assume that all CO is basically consumed and you have CO2 only. Okay, but because now CO2 dissociates also back to CO and O2, so you will have a mixture of CO2, CO, and O2. In addition, the oxygen may dissociate to oxygen atom at very high temperature. So you will have a mixture of this. So our intention is to predict what would be the composition of the mixture. Okay, so we will to get this, we will use second law of thermodynamics, but in the form of change in Gibbs free energy rather than change in entropy. You had seen this problem earlier in terms of entropy. Okay, so what is the Gibbs free energy of this mixture? This is equal to so first of all, this mixture of gases we are considering is at certain temperature and pressure. Okay, now the Gibbs free energy of this mixture is basically equal to the molar Gibbs free energy of individual constituent multiplied with the number of moles of that constituent. Okay, as you write the entropy of the mixture, if you remember. Okay, now this is basically the chemical potential. Okay, and this is equal to so what does this mean? See, earlier we had defined the Gibbs free energy. If you see this G, still it is not coming. This G over bar. Earlier we were writing G over bar, that is the Gibbs free energy per mole of a substance. You can write this if you have only a single component system, but now you have a multi-component system. Okay, so here we define the chemical potential or G over bar as partial derivative of the the Gibbs free energy of the mixture with respect to the change in number of moles of that particular constituent, that is I, while all others remain constant. What I mean is that let's say you have a mixture of CO, CO2 and O2. Okay, so how much Gibbs free energy would change if I remove or introduce 1 mole of CO? Okay, while CO2 and O2 number of moles of CO2 and O2 are remain same. That is basically equal to the chemical potential of CO. Okay, so now if we consider the definition, here okay, this I can write take some time. So okay, so what we are trying to do here is we want the Gibbs free energy of ith species at temperature Tp. Okay, now the Gibbs free energy, like the entropy, has been tabulated for different gases. Okay, but at atmospheric condition, this is what you know for different temperature, as in the case of entropy. Okay, so this is known. What we want to find is this. So we want to relate these two. That is why, like Gibbs relation, here we are developing a relation. So here, under equilibrium condition, du plus PdV is equal to dQ. So this part is basically equal to 0. So this is gone. So you have VdP minus SdT. Okay. So now if I consider these two states, that is ITP and ITP naught at the same temperature, and I want to relate these two, then I can use this relation here and write this as VdP, because in that case this term is 0. I hope you are able to get what I'm saying. This part is 0 because we are considering the two states at the same temperature. So that is why I can write GITP is equal to GITP naught. This is obtained from the table, plus now I can use ideal gas equation and write V as R T by P and integrate this. So I get R T ln Pi by P naught, as we had done in the case of entropy, if you remember. Some time to okay. It is taking some time to save it today. Are you able to follow me?
Yes, sir.
Hello? Okay, good. Okay. Okay, let's proceed. So now I can write the G mix, or the total Gibbs free energy of the mixture is equal to okay. Here this should be, I should be writing Pi. You know the reason why I'm writing this, correct? This is because we are considering the partial pressure of the gas. So now I will write this expression here. So this becomes Ni Ei P naught plus RT ln Pi by P naught. Okay. So now we know that for fixed temperature and pressure, overall pressure, under equilibrium condition, the net change in Gibbs free energy of the mixture should be equal to 0. And that is what is second law of thermodynamics. Okay, now in terms of G. So the change in Gibbs free energy can be less than or equal to 0. For equilibrium condition, it is equal to 0. So now if we differentiate the above, we will get first you differentiate this, then you differentiate this one. Plus so now I can write this everything as There is some problem today. I don't know why it is doing this. It is unable to save it quickly. So, yeah, what I mean is that here in this case, this part will be, we can show that this part is 0. This is because here you can see this term is a constant. Similarly, this term is a constant. So they are 0. Now what is remaining is NIR, NIDRT ln Pi summation. Now this is equal to RT is constant, NIDPI by Pi. Okay. Now this is equal to RT. Ni by Pi is essentially equal to N by P. You know why? Why Ni by Pi is equal to N by P?
Mole fraction.
Yeah. So Ni by N is basically equal to mole fraction, which is equal to Pi by P, partial pressure to total pressure ratio. Now this gives us summation of dPi is 0. This is equal to 0 because summation of dPi is 0. Okay. Why summation of dPi is 0? Because summation of Pi is constant, right? The total pressure is constant here. Okay. So that is why dPi is 0. So that is why the second part is 0. Now consider a general chemical reaction. So this is a general chemical reaction. Now, we know that the chemical reaction proceeds at certain rate. Okay. And that rate is a constant. Okay. Now, that rate is related to the rate of depletion of reactants and rate of production of products. So what I mean here is that this. Okay. So what does this mean is that, so these are basically the molar coefficients. So if we consider again, let's say this reaction. Okay. Now, when the reaction starts, there will be some reduction in the number of moles of the reactants, that is CO and O2. Okay. Now, if we normalize that with the molar coefficients, that is here 1 and here half, okay, that ratio is basically equal to the rate of the equation, and that is equal to rate of production of CO2. Okay. So in this case, I can write okay. So this is basically equal to the rate of the reaction. So if I invoke that in this equation, okay, then if we invoke that here in this equation, then I can replace dni by the molar coefficient. You will soon understand why we are doing this. Okay, again, our objective is to predict the composition of the mixture. Okay, so now here I can rearrange things. Okay, here, and I can write this as everything is slow. I hope you are able to get this step. Sorry, there is some problem today. Uh, so what I have done is here I just rearranged this equation that you see. Okay, I have brought these terms which are known to right side. Okay, this term is known because we know the Gibbs free energy under standard pressure, that is atmospheric pressure, and for different temperature. This we can get from the table. R is the universal gas constant, T is known, the temperature that is given. So on left hand side, what you have is Pi divided by P naught. Okay, and what is Pi by P naught? It is the partial pressure of the the individual gases divided by the atmospheric pressure. Okay, so I can rearrange this, and this term, this symbol pi denotes product, like sigma denotes summation, pi denotes product. So here I can write it's very difficult today. So this should be P. This term, what does this term represent? The first term in this bracket represent what? Can anyone tell me?
Change in the Gibbs free energy at the standard conditions.
Correct. So the bracketed term represents the change in Gibbs free energy under standard pressure at the given temperature. Okay. The first term within this bracket, I mean this one, is basically the sum of Gibbs free energy of the products. The second term is sum of Gibbs free energy of the reactants at the same temperature but at atmospheric pressure. Okay, and that is basically equal to delta G naught, which means change in Gibbs free energy under standard pressure at the given temperature, which is a function of temperature. Okay, so this is known, numerator is known, denominator is known. Okay. Now,
Sir, won't there be a ln on the left hand side?
yeah, there should be an. Okay, so what is Pi by P?
Partial pressure of the ith component.
Partial pressure of the product divided by the total pressure. Okay, on the numerator you have everything related to the product. Denominator you have everything related to the reactants. Okay, so this is basically equal to what? Pi by P is what?
Mole fraction.
What is Pi by mole fraction? Okay, so you have basically the mole fraction of all products raised to the power of their respective molar coefficient, the product of that divided by mole fraction of the reactants raised to their corresponding molar coefficient multiplied with P by P naught. What is nu IP minus nu IR? Nu IP, sum of nu IP is basically equal to sum of number of moles on the product side minus nu IR is sum of number of moles on the reactant side, and this is equal to e to the power of, there should be a minus here. I forgot, so you will get this expression. Okay, it looks complex, but let's consider a simple case such that it will be clear to you. Now let's consider again the same problem, this reaction. So we have a chemical equilibrium reaction between reactants A and B and products C and D. A, B, C, D in small case represent their molar coefficients. Okay, so now I can write according to the above equation, the mole fraction of A raised to the power of A, mole fraction of B raised to the power of B divided by is multiplied with P by P naught C plus D minus A minus B is equal to minus delta G naught divided by RT, where delta G naught, can anyone tell me now, if you know what these species are A, B, C, D, and if you know their Gibbs function under standard pressure at the given temperature, what will be the expression for delta G here? Can you hear me?
Summation of
Hello?
Ni into G of I P naught.
You don't have to tell me in terms of Ni. What is the final expression? C times G C, right, at the given temperature, and P naught plus D times G D minus A G Is it clear?
Sir, won't the left hand side be the reciprocal?
Reciprocal of what?
So means in the formula that the product is on the numerator and reactants are on the denominator.
Sorry. Yeah. Here, no. Thanks. This should be on numerator. You have the products. On denominator, you have the reactants. Okay, right. So now you understand. Uh, okay, now you understand. So finally, this is the essence of what we were discussing. So if a chemical equilibrium reaction is given, then the composition of the final composition, okay, is related to temperature, pressure, and gives free energy using this relation. Okay, is it clear? So now if you consider, let's say, the same reaction. Please note that here you have forward and reverse arrows both. This means you have both reactions going on simultaneously. Okay, but I write it this way. Okay, so now can you write the above equation for this reaction? What should I write? What do you have on product side?
CO2.
CO2. So X CO2 power 1 divided by XCO XO2 to the power of half. Okay, P by P naught to the, what should I write here? What is the exponent of P by P naught?
Minus half.
Minus half. Just 1 minus half. So minus half. This is equal to e to the power of minus delta G naught by RT. Here pressure and temperatures are given. Okay, now what is delta G naught here? G CO2 at the given temperature, standard pressure, minus G CO minus half G O2. Okay, so this is the equation, okay, that relates the final composition of CO2, CO, and O2. And this, you know that for a given temperature, this side or this right hand side is a constant. And this is known as equilibrium constant. This is very important. Okay, and interestingly, you see that it depends only on temperature, not on pressure. Why?
Because G naught is set at 1 atm pressure.
Correct. So G naught means it is always at 1 atmospheric pressure. The reference is that only. Okay. All other parameters change with respect to temperature only. So Kp is basically a function of temperature, and this is known as equilibrium constant. So higher the equilibrium constant, for a given reaction like this, it means more products are formed. Lower the value means the reaction is not happening. So the products are not being formed. Okay. So for example, if you take CO and O2 under atmospheric temperature, under atmospheric pressure condition, the value of Kp you can calculate. Okay. And that will be very small. It will be say 10 to the power minus 3 of the order of that. But if the temperature is very high, let's say 3000, its value will be very high. Okay. So let's say 100 or 1000, something like that. Okay. This means more products are formed. Okay. Now, you know, okay. Now, my question is, how will this change if I write the equation like this? Okay, you think about that. Okay. Now, what is our objective here? Our objective is to find okay, have we achieved that? Any answer? Have we have have we achieved the calculation of mole fraction of different constituents? Any answer?
No, sir.
No. Why not?
Uh, because in the left hand side we basically have the product, means a product of the mole fractions. Uh, so it is not possible at this point to separate them out.
Because we have only one equation and three.
Very good. So you have three unknowns in this particular case. So you need three equations, obviously. So this gives you one equation. Okay. What is the other equation, general equation that you know? Can anyone guess?
Summation of the mole fraction will be equal to 1.
Very good. Yeah. So this is basically the second equation. Okay. So this means we need one more equation to solve. So how do we get that? Okay. In this reaction, do you think the number of atoms of carbon and oxygen are conserved? See, initially you had CO and O2. Finally, what you have?
Mixture of CO, O2 and CO2.
CO, O2, CO2. Okay. But the number of atoms of carbon and oxygen must be conserved. Number of atoms. Okay. So initially you had one carbon atom and finally also you had one carbon. If there is only CO2. Okay. So assume for a moment that this reaction is complete and you have only CO2. Okay. Then number of atoms of oxygen is 2 initially and finally also 2. Okay. Now consider the case where you have this equilibrium reaction going on. Do you think the number of atoms of carbon and oxygen will be conserved?
Yes.
What is your answer? No answer. The number will always be conserved. Where would that atom go otherwise? See, initially you have carbon in the form of carbon monoxide, and finally you have carbon monoxide and carbon dioxide. But the number of atoms must be equal to the number of atoms must be same as in the beginning. Okay, so in this case we can consider the ratio of number of carbon and oxygen atoms. What is this ratio initially? Let's say you have CO and O2 initially. What is the number of carbon atoms you have?
1/2.
1/2, correct. Number of carbon atom. So you have CO and O2. Number of carbon atom is 1. Here 0. Number of oxygen atom here is 1, and here you have but here we have half O2. Okay, so that is why it is again 1. Okay, so this ratio must be constant throughout the reaction. Now let's assume that finally you have n number of moles of CO2, n number of moles of CO, and some moles of O2. Okay, this is the number of moles. Now you tell me how many number of atoms of carbon is present. How many number of atoms of carbon is present in this NCO2 number of moles? Okay, in 1 mole
into
Avogadro's number. So that Avogadro's number is always constant. So you need not consider that here. Okay, so this should be NCO2 in this case plus NCO actually multiplied with Avogadro number. Okay, divided by how many number of atoms of oxygen is present in NCO2? 2 times NCO2, right? Right, because this is CO2. In 1 mole of CO2, you have 2 into Avogadro number of oxygen. Correct? So this is 2 NCO2 plus here
2 NCO.
Why 2? Only NCO plus
N twice
2
NO2.
O2. You don't, in order to write this, you don't have to look at the equation at all. You just consider what are the constituents. Here you have half O2. This does not mean that here you should put half O2. Okay. We have just assumed that these are the number of moles, and accordingly we have written the total number of carbon atoms and the total number of oxygen atoms. That's all. Now this is the number of moles of different species. Now if I divide this with the total number of moles, that is NCO2 plus NCO plus NO2, then what I will get here? Mole fraction of CO2. Mole fraction of CO divided by right? Okay, so this gives me the third equation. Okay, so you can solve these equations, these three equations, which may be nonlinear, especially because of equation 1. Okay, and get the 3 mole fractions. Is it clear? So the most important thing here is writing the expression for equilibrium equilibrium constant. Then you have this general equation. Then you have atomic balance equation. Okay. Now, for those cases where the number of moles does not change, for example, let's say in this equation, A, B, C, D all are 1. Then what will be the exponent of P by P naught?
0.
0. So equimolar reaction have 0 dependency on pressure. So pressure does not play a role for that. And also for the case where pressure itself is equal to P naught. If P is equal to P naught, then this term disappears again, right? So for these two cases, pressure has no role. Okay. So now you can do this for different temperature and pressure. Okay. We can do this. Then if I plot XCO versus pressure for different temperature. Okay, if I fix the temperature and if I increase the pressure, then I will get a curve like this. Okay, so what does this mean? This means that if I fix the temperature and increase the pressure, the mole fraction of CO reduces. Okay, what does that mean? More and more CO are consumed, right? Similarly, if I increase temperature at a given pressure, then the mole fraction of CO increases. It means more and more dissociation occurs. I hope you could understand what I'm saying. See, if I fix the pressure and if I increase the temperature, okay, and for each of those state points, I calculate this mole fraction. I see that more and more CO are produced. It means the reverse reaction is more important. That is, the dissociation is more important. As we know that at high temperature, dissociation is important. Okay, so similarly, if I keep temperature constant and if I increase pressure, then mole fraction of CO reduces. This means the reaction is proceeding mostly in the forward direction. That is, more and more CO2 are formed. Okay, and just a moment. And a system. So finally, the change occurs such a way that it tries to minimize that change. And this is known as Lee-Chatelier principle. Okay, so we will continue this discussion in the next class. So, in summary, what is the essence of today's discussion? Clicking something happens. Is basically the information on the equilibrium constant. Okay, I could have simply written this equation without giving all the previous details, but that was essential to show you how second law of thermodynamics is applied to calculate the equilibrium composition. Okay, so this equation is the most important one that you should remember. Okay, this is for a particular example. Okay, so you should be able to write this equation for any equilibrium reaction. Okay. Okay, do you have any queries? Hello? Can you hear me?
Yes, sir.
Okay. Do you have any queries? Okay, so I think the best way to solve your queries is to solve the problems only. So I have already sent you tutorial 5. Please go through it, okay, and start doing the problems. Okay, and also go through today's lecture again to understand the equilibrium constant. Okay, this is something new that you haven't studied earlier, but it is not difficult. So mathematically, only that equation for equilibrium constant is what you need to remember eventually to calculate the composition at equilibrium. Okay. Okay, so thank you. We'll meet tomorrow.